So we are seeing about the fixed stripe multi-bit trie. Okay. So in each level, we are going to have a fixed bit that is being given as the stripe here. Okay. So as written here, so level 1. Okay. So level 1 is taking 3 bits for all the branches. Level 2 is now fixed with 2 bits. Okay. So we can always see 3-bit expansion at the level 1 and 2-bit expansion at level 2. And when we combine all these levels of expansion together from the top to the bottom, because a part can be calculated only from the root node towards the leaf nodes, right? So when we try to look into the aggregation of all the part from top to the bottom, that will always fall in line with the expansion, what is being found, what is being done at the previous stage. Okay, so we did some prefix expansion, right? So that's seen here. One second. Yeah, so this shows the prefix that is being found in the original subtrie and how it is being transformed with the help of this prefix expansion. Okay, so with this prefix expansion only, we are going to proceed with the fixed stripe multi-bit trie, and but not not crossing the boundary of the expansion. Okay, so we are going to fall within the boundary of the expansion. Okay, so I'll redraw the tree since it is not that clear. Okay, so this is with 2 bits. Okay. So now I'm going to redraw the tree. Okay, so we'll have the root node, and then the first level is being set with how many bits? 3 bits, right? So we are going to have a possible combination of zeros and ones at the 3 bits length. Okay, so that would be the branches. So we can have 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Right? Then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are the possible branches with 3-bit combination. Right? So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay? So 8 branches will be from the root node. Okay? So, okay. So we'll take from the root, we'll proceed with 0, 0, 0. And next is 0, 0, 1. And next is 0, 1, 0. And next is 0, 1, 1. And next is 1, 0, 0. And next okay, so so next is 0, 1, 1, 0, 0 is over, and this is 1, 0, 1, and next is 1, 1, 0, and next is 1, 1, 1. Okay, so we can see from the expansion 0, 0, 0 is from the expanded prefixes. You can see. Okay, I'm just bringing it all into one minute. You can see expanded prefix 0, 0, 0 is now P1, prefix P1, right? So we can move to prefix P1. Okay, so that is a prefix. So we have to shade it. And 0, 0, 1, 0, 0, 1. Okay, 0, 0, 1 is prefix P3. Okay, so we can write it as P3 here. It is again a prefix. So it's P3. and 0, 1, 0. 0, 1, 0 is it's P1. So 0, 1, 0 is P1. That's again a prefix P1. And next is what? 0, 1, 1. 0, 1, 1 is again a prefix P1. So it's again prefix P1. Okay, so this is P1. And the next one is 100. So 100 is prefix 100. Yeah, so it's prefix P4. Prefix P4. You can also see in prefix P4 also 111 is again getting repeated, and it is an captured. It is an expanded prefix that is captured by the existing prefix. Okay, so we can remove here this also. This could also be removed here, and 100. 100 can remain 110. So 110 and 101, say they are unique. So let's see in the example, it says 100. So 100 is corresponding to the prefix P4. So we can write here as P4. So it's P4 here, the prefix. And 101. 101 is again P4. Okay. So we'll write it as P4. Okay. And 110 is corresponding to again P4. P4, and 111 is corresponding to P9. Right? Okay. So the first level is over, and you can see from the root, all the branches that emerges carries the same length of bits. Okay, the length of bits is same, and so in the first level, the number of bits associated with the first level of this multi-bit trie is 3 bits. Okay, so level 1 is carrying 3 bits sequences, and from level 1, then when marching towards level 2, the number of bits that could be accommodated is 2 bits. So that is what is being fixed. So 2 bits. So the possible combination are, let's see, from P1, okay, we have to mark the other prefixes. So P1 marking is completed, and P3 marking is completed, and P9 marking is completed, and P4 marking is completed. So the remaining prefixes that are not being marked so far is P2, P5, P6, P7, P8. Okay, so these are the things that has to be included. Now let's see P2. P2 is an expansion of 0, 0, 0. From P1, P2 can come, right? So because P1 is 0, 0, 0, from here you can have the remaining bits. 0, 0, 1. Okay, so 0, 1. When you try to append this, you can find from the root it has to be coming to down. So first 3 bits are 0, 0, 0, followed by 0, 1. Okay, so 0, 0, 0, 0, 1 is yielding to prefix P2. So we can mark here as P2. It is again a prefix P2. The remaining things also you can do, but they become non-prefix nodes. Okay, so the other combinations 1, 0, 1, 1, maybe 0, 0. So these are all leading to nodes, but they are non-prefix nodes. And if you want to find the path from the non-prefix nodes, then you have to look up to the ancestor for getting up the information about the routing and all. So this is how the tree is being organized in a fixed stride multi-bit trie. Okay, and So let's look with an example. So if there is an incoming bit, so 100111, okay. So first we are going to search. Now what is the protocol according to the level we have fixed? So level 1 considers how many bits? It's 3 bits. And level 2 considers how many bits? It's 2 bits. Okay, so this is the incoming destination IP prefix. So this has to be divided according to the level which has been fixed here. So first level say divided into 3 bits. So first consider 100 alone. Sorry, 100 alone. Okay, so with this 100, which route you can take from the root node? So 100 is taking us to this path. Okay, it will take us to P4. And next is the next 2 bits. So from P4, you have again a combination of 4 possible opportunities with 0, 0, 0, 1, 1, 0, 1, 1, and they are leading to P5. This is again leading to P5, and this again leading to P6, and this again leading to P6. Okay. So this is the combination. Now the next level of bits is 2 bits. So we have to focus on the next 2 bits, that is 1, 1. So when 1, 1 is taken, you can see the path ending up P6. So P6. So now first, by looking into the first 3 bits, the best prefix that has been matching is P4. And since we have more number of bits to inspect, we cannot finalize P4 as the best matching prefix. We have to discard that and come down for searching of the next level. So it is 2 bit, 1, 1 is considered, and P6 will be now considered as the best matching prefix. So the final answer, okay, the final answer for the best matching prefix for the incoming destination IP prefix 1001111 is P6. Okay, so here from this fixed stride multi-bit trie, you can always see that the number of memory accesses required is just 2. Okay, so when you have to do the same with normal binary trie, then the number of access you have to do with the memory is, because it is single bit by bit instruction, so it's 1, 2, 3, 4, 5. So then with the normal binary trie, the number of for memory access, okay, I'm talking about memory access here. Normal binary trie, the number of the memory access that would have, because the last bit is 1. We don't have the further division of further expansion of subtrees, okay. So we are closing the search on the 1 bit itself. We are not going to proceed further because there is no descendant branches emerging from P6. And in the binary trie, you can see the number of access for finding this path for the for fetching up this first 5 bits will take 5 times we have to do memory access. But in the case of fixed stride multi-bit trie, fixed stride multi-bit trie. Okay, it's multi-bit trie. So here you are using only doing memory access only 2 times. So there is a decrease in the level of memory access also. Okay, so when you work with the concept of a fixed stride multi-bit trie, the number of search time, the search time is given, the complexity of search time is mentioned as big O of, or the order of O, W by K. So K, where K is the stride, W is the length of the address, length of the IP prefix address, length of the IP prefix. Okay, so this is what is being given as the search complexity that happens while traversing into a multi-bit trie, that is a fixed trie. So next, let's have a look into the update algorithm. So updating is nothing but inserting a new prefix could be an updation, or modifying the existing prefix could also be another updation. Okay. So let's consider an example. Like we need to insert first. So assume that we are going to insert prefixes like 1100 star and 10111 star. Okay. So to this fixed stride, if you want to insert these prefixes, since we have P1 to P9 already listed, let's name it as P9, sorry, P10. So let's name it as P10. Let's name this as P11. So this new prefixes, if you have to fix it inside the fixed stride multi-bit trie. So let's see how this insertion is happening into that tree. Okay. So this is the tree given, right? That is the tree. Yeah, this is the tree given. So we have to insert, yeah, 1100 and 10111. Okay. So already in the first level itself, we have 000 is there, 001 is there. You can see the first 3 bits of the incoming prefix P10. Okay, it's 110. So which part you need to take? 110 is this part. Okay, P4. So from P4, we'll have the expansion. Okay, so from this P4, there will be an expansion into the next 2 bits. Here there is no 2 bits, but there is a possibility of another bits coming in. Why? Because there's a star. Okay, so it could be always attached under P4 with the label 0, 0, 01, 02, 1011 combination. Okay, so that would be, so this could be the part. So from here, there will be 4 parts emerging. There will be more combinations of nodes that carries with 00, 01, 10, 11. So this is the right way where it gets inserted. Okay, and next is about the implementation. Okay, so you can implement this kind of stride multi-bit, like fixed stride multi-bit trie, and at each entry, as we have learned earlier, there will be 2 information present in every node. The first part carries the next hop information, and second part will be a pointer to the sub-trie. Okay, so if you want to implement, you can use it in any of your search algorithms. A search requirement could be met with the help of this multi-bit trie. And so the only concept you need to have in your mind is the search time has to be reduced and the memory access has to be reduced. And the choices of strides. Okay, so there are 2 types of strides, right? The first one is fixed multi-bit trie, and second one is variable. So fixed we have seen already. So now we are going to see the variable stride multi-bit trie. So when do we go for this variable stride multi-bit trie? When do we go for this variable stride? Because fixed stride we have already seen, which means in every level, the number of bits that emerges from a particular root node will be equal. Okay, and in level 2, another set, a number will be fixed as a stride length based on which the branches will be. And in variable stride, we can always have in one single level itself, okay, you can have a combination of all length. Okay, for example, in level 1, if it is 2 bits stride, and level 2 can be of either 2 bits or 1 bit. So this could be the combination of strides. Okay, and so when in case, like if you want to have some dynamic programming based approaches, then you can choose the type of stride you want to proceed with. Like either it could be you want to have a variable stride. When it comes to dynamic approaches, then obviously you need to fall in line with the variable stride approach, right? So according to the need of your programming, according to the need of the application, the selection or the choice of the stride could be either it could be a multi-bit variable stride multi-bit trie, or it could be a fixed stride multi-bit trie. Okay. So thank you so much.